11 years ago, I was working at this company, OLI, and their sales were like lousy. And I said, well, you know, I could sell this software better than I know it from the inside out. That's how I ended up being here. Who is OLI? OLI is a very unusual company. It's based in New Jersey, and it has spent 44 years devoted entirely to electrolyte thermodynamics. The founder of OLI is Marshall Rafel, and he decided, when we met at Exxon, and he decided that he was so interested in electrolytes because they're very poorly behaved mathematically. And he became very interested in the challenge of how to converge electrolyte solutions. And that's kind of how the company grew. So its mission, as I say, it's a very unusual company. Its mission is to further the electrolyte science. So in a way, it's a quasi-university, but it does have a commercial arm. Core competency, electrolyte thermodynamics, process simulation, and we also do corrosion science of the chemistry in contact with bulk solution. Primarily, if you work with OLI, you work through their products. You work through either the OLI Studio, which has a bunch of sulfur components, or you work through electrolyte flowsheet simulation, where you're developing a water plant and you want to work inside a commercial simulator, such as Aspen Tech or Pro2, and they have their own simulator as well. So what am I doing here? Well, actually, our mission is a little bit different. Our mission is to help clients address water chemistry issues. I'm a principal, my partner AJ is a principal. And we have to thank AJ. He probably would be a better person to come because I want to talk about applications today, and he's a much better applicant. He's a process simulation specialist. But anyway, he's helping create most of these slides. So what we're doing is we are basically trying to apply OLI. We do that exclusively with OLI technology for sales training and applications consulting. What we offer is electrolyte process simulation experience. Why do you want to use simulation, and especially any simulation is true, but why do people use simulation to begin with? What we're trying to do is we're trying to duplicate a physical process. And we're trying to do that through principles that we call it first principles with applying electrolyte thermodynamics, and that's how we're trying to do it. So through chemistry and mathematics, or you can say physical chemistry, we're trying to duplicate what it is that you're seeing in reality. That can apply to production chemistry, it can apply to water treatment. Why people want to do it is if you can duplicate a physical process, then you can identify problems before they occur. Although a lot of my case studies are talking about problems after they occur. You can also predict where to treat for scale, to find safe ratios if you're mixing waters, and also to screen out different treatment methods. OLI is more interested, or is more focused on understanding what the problem is than on understanding what the solution is. But you do have to understand the problem before you can find a solution, and they're really good at ferreting that out. And we'll talk more about that. I really want to thank Steve and Vince, especially Steve's talk, because he took a lot of the pressure off me in terms of saying what is scale, how does it develop, how are particle sizes, et cetera, et cetera. So we don't have to go too much into that, but we'll go a little bit into the underlying science. Then we'll talk about the limits of when you have this kind of model, when you're worried about scaling, what are the limits of scale prediction? Then we'll talk a little bit about case studies, and then we'll talk about some of the challenges. I have two parts to this talk. This is the first part of my talk. It's about scaling. I'm going to give a little bit of talk, and after we talk about scaling, into the corrosion simulation. OLI fits high-end. It's high-end in scale prediction. It's high-end in corrosion prediction. Our corrosion tool is a little bit of a research tool. Our scaling tool is much more applicable to day-to-day problems. But we'll talk about both. Okay. So we've already understood this. Scaling tendency. What we say scaling tendency is we call it a thermodynamic driving force for a solid to precipitate. Thermodynamics works on energy. It's all about how to find the right energy of a state, okay? So what we say is a scaling tendency, if it's greater than 1, it's going to precipitate. Less than 1, it's going to dissolve. If it's at 1, if it's at saturation, which is an important part that determines your solubility, then it's not going to dissolve or precipitate. We call it scale tendency or scale ratio or saturation ratio or supersaturation. If you see the word index in a scale tendency, it means that it's the log. So we work with the scale tendency as a number, and then you can also work with the log, and that's called the scale index. We've talked a little bit about Langmuir, Stiff Davis, Odo Thompson. We didn't, well, let me stop there. We could start using can calculations, we can move into empirical methods, and then we can move into the full speciated model. So when you're working with a simplified model, you can calculate this. Classically, what they have been is to calculate a measured concentration divided by the concentration at an equilibrium state, and if it's greater than 1, you're going to scale. So that's been the kind of rudimentary way you could say it. When you look at it from a thermodynamic point of view, what we're saying is the activities divided by the abilities. What does that mean? So in thermodynamics, we talk about a reference state and then an excess state. We talk about an equation of state to define an ideal state, and then when you're past that, we talk about excess properties. So reference state, excess properties. So when we talk about the solubility product constants, we're really talking about the reference state. Now the reference state comes, get some water, and I apologize, I got this cough out of nowhere a couple days ago. The reference state comes from 1 degree Celsius, 25 degrees Celsius, 1 atmosphere, infinite dilution. Infinite dilution is the key. Because that means that ions are not attracting each other. Infinite dilution means that there's no effect, they're not having an effect on each other. When you're in the excess properties, when you're in the activity state, ions are impacting each other. It's not just the calcite, it's not just calcium ions and carbonate ions, but it's all the ions in your soup are impacting each other. So what we're describing is we're saying the activities, the ion activity product divided by the solubility product. And that's the definition of scale tendency in a speciated. Okay, a little bit more, and then we're going to stop with the slides. So if we just take barite, and barite breaks into the barium and the sulfate ion. And so then here we're looking at activities. Activities are based on the molality of the solution with the activity coefficient divided by the K value. You don't really need to remember this. All you really want to think about is activities divided by solubility, excess properties divided by reference state. And that's actually what produces the scale tendency on a first principles basis. So we talked a lot this morning. I was like biting my tongue. And I also am just totally embarrassed to say that I should have had French Creek in here, and I really apologize. And if anybody goes back and tells Bob that I didn't, I will come find you, because he really should be in here too. And I don't know why he's not, because this blah blah. Anyway, so why do you want to use a computer model like OLI, or why is it important? There are plenty of good indices. Langmuir did have some problems. It went down to Stiff Davis. They fixed it. Stiff Davis was taking more of the common ion into effect, so he was staying over there. Odo Thompson is a great, that actually is the Rice University Product Consortium, and they actually worked really well on a lot of their solids. And a computer model like OLI, what is the advantage? I would say, by the way, Odo Thompson's probably in this box already, but I don't really know. But basically, when you have things that are not predicted in your water, if it goes beyond the standard oil field scales that we've studied traditionally, then it's really good to be in the speciated model to be able to just account for what's in your water sample. So it's a higher tech way. Once you've got all those great water analysis methods that Vince was talking about, it's a higher way to get into, a more precise way to get into an actual scale tendency. So what I'm showing here is actually what I said about Marshall Raffel. He was so interested in the poor behavior of electrolytes, the poor mathematical behavior of electrolytes. How could you build your life on the poor behavior of electrolytes? But evidently that's what we've done. So we're looking at a set of isotherms at the temperature range from 10 Celsius to 150 Celsius. And it's just calcite. It's calcite along with it's calcium chloride, the carbonate, and H2O. What's important about this slide and why you want to talk about it is the difference in behavior. Look at the slope of the green versus the slope of the gold. The gold is a higher concentration with more CO2. But this is not easy to predict. So methods that are less robust, just on a system of, you could say, but I only have carbonate, I only have calcite as my solid, but really the behavior is so poorly behaved for mathematics that it's hard to predict this in a less robust model. So that's kind of the point that we're talking about here. Okay, that's all the good news, but there is some not so good news about scale tendency, which is it's only equilibrium based. It has a huge disadvantage in that kinetics and inhibitors are beyond the scope of a thermodynamic model. I'll talk a little bit about why. It's easy to understand why. That's the cough. So all scale prediction models are equilibrium based, and you need to add on something to calculate kinetics. Kinetics can be pretty simple. You can say, well, we'll talk a little bit about what that could be. I'm so glad Steve talked about this because I'm not going to talk about it. And actually Vince did too, the difference between a scale and a deposit. We don't actually go there. We're only talking about energy. We're only talking about the thermodynamic driving force for scales to precipitate. Nucleation is an issue. Does it have something to latch onto? Is it going to latch onto the wall? I was Vince's description where you put the one drop into the one piece of the scale to let the nucleation start, and whammo, everything starts. So there's all kinds of mechanisms for scale buildup when you get to finally understanding what's going to happen. Is scale going to be a problem? All we really want to talk about as thermodynamicists is basically, is the driving force of, do you have a problem? Is your system going to have a problem? And then, sure, all these things are going to be kind of hit to try to decide whether or not you have a problem in terms of crystal growth and things like that. Okay. So one of the things that we do as consultants, because remember I said that AQSIM has started to sell OLI software, we also consult with OLI software, so we're applications people. We take information like this, and we've created this particular slide for our own reference, and what it's doing is for the oil field scales that we are most interested in, the halite, the gypsum, the calcite, the barite, and we've just developed timetables for kinetics. This is a log-log plot. It's saturation ratio versus the time, and you can and the symbols are the scale tendencies, the saturation indices. Okay, so or not indices, the saturation tendency ratio. So that means that your scale tendency on gypsum, for example, can be much higher. It can be up at 10 if your induction time, if the time that in seconds is only going to be 10 seconds. What that means is if you have something flowing really quickly, it's not going to have time to nucleate and adhere. So even though we're worried only about the thermodynamic driving force, you can see that there's different ways that you can calculate. Okay, even though the program said 4, the scaling tendency is 4, is that a problem? Well, no, it's not going to be a problem. It depends on how fast it's flowing or how stagnant it is. It depends on a lot of things. So what we're going to tell you is 4, and then you're going to figure out, okay, is that important? Okay. Also, inhibitors. This is an interesting slide. If you look at the 3 curves here, this pink one and the green one and this blue one, that's the growth of calcite on a metal without PPCA, right? Okay, so they put an inhibitor on this, and then you can see much better behaved. So we don't do this kind of inhibition. And why don't we do it? Because we had a great description of what inhibition's doing. It's not thermodynamic. It's not working on energy. It's working on interruption. And we don't model that. You don't know my models that. Scale tendencies don't model that. So kinetics and inhibitors, you kind of have to get extra. You have to get it, and where you usually get it, by the way, is from chemical treatment companies. But you don't really know what you have, so you don't know how to treat it. Your chemical treatment company doesn't necessarily know what you have, and that's really where we come in. So why do you need us? If you're going to go to the chemical treatment company anyway, why do you need us? Well, you really need to understand the problem. I love Vince's things about the known and the unknowns, and the known known and the unknown unknowns, and all of that. Because what OLI offers and what a good scale tendency, any program that can properly predict scale tendency or pH, excuse me, and I do consider French Creek a good program like that, then they are able to give what you need, which is mass balance and scale tendency. That will create if you apply it correctly, that'll really let you show you what your problem is. So let's talk a little bit, how do we do that? We can do that, we can use it as a simple well scaling analysis. We can use it if we're mixing waters and we want to try to understand will waters mix compatibly or not. And we can do it for treatment after we've mixed, or after we've produced them. So that's why we want to use it or where we want to use it, and let's look at how. Let's look at some examples. Okay. So I have 3 examples in the scaling tens. In these, 2 of them we picked because they were already made as SPE papers. One of the problems with our industry is that everything is done under non-disclosure agreements, and so we we're limited by what we can say. The third one that we picked, we've changed the names quite a bit, although it did happen in Australia. But this one, there was a well, and it was plugged, and they wanted to understand how to treat it. So before you just kind of go ahead and do what the treatment is, you have to understand why did it plug and where. So they knew enough that it was plugged by sodium fluoride. Oops. Sorry. And they had a water sample. I loved water samples don't really help very much. Because why don't they help very much? Because it's already done. Like if you've been precipitating in your well, by the time you get to the water, there's nothing left. So what do, right? It's kind of like you have to recreate. So basically, we got a water sample. The water sample was pretty innocuous as far as we could tell, and it didn't really show any other problem. So what we had to do, and this is why I asked the question about formation, you have to kind of recreate what happened. You have to recreate it from downhole up, or formation up. Now, how do you do that? Well, you have to know information. You look first of all at your well sample, but you also have to know information about your formation. So if Marcellus Shale is all the same every place, then you know it. But if you don't know it, if you don't know that, or if there's an area that's particularly a little bit funky, or if it's different, you try to understand what the formation is, and you recreate. You run a saturation calculation, and you recreate the reservoir, what we call the reservoir brine. So you recreate what the brine is, and then you pull it up through different temperatures and pressures. Now the strength of thermodynamics, and why thermodynamics is an important science, is that you don't lose mass, right? So we're going to keep the mass. So we're going to create the mass from the downhole conditions. We're going to pull it up through different temperatures and pressures. And guess what? As it goes through pressure drop, as it goes through temperature changes, the state of the solids are going to change. So what was vapor, or what was basically what was vapor in the formation as it's coming up and it's cooling, water's going to condense, things maybe get diluted, solids maybe form out, depends on a particular solid. So what the only thing we did here was we reconstructed the reservoir brine, and then we pulled it up through a series of temperatures and pressures. That's the approach. This, what we say about here, phase partitioning. That's the other thing. So it changes state. So thermodynamics says that if you understand the state of one situation by conserving its mass, you can predict the state over here, and over here, and over here. And as the state changes, nothing else is changing. It just depends on what the energy of the system is. Temperature and pressure are being withdrawn or added. And that's what determines how you think about things. So what we were able to do is we were able to create this graph of depth. Now, we didn't actually use depth in the program, because if you think about a program, it's totally talking about temperature and pressure with thermodynamics. So we only think in terms of state, temperature, pressure, and composition. So we drew it through a series of temperatures and pressures that simulated the well, and we started to see what the scaling tendency was doing. So one, and then you can see it starts to come over here, and this is where the problem is. And that's how this case was worked. And what we were able to do from that was we took the temperatures and pressures back, and we were able to understand that there were 2 places. There was a plug that formed entirely in the tubing at that particular spot, and then there was scaling along the tubing more, and then it also plugged up there. We could do that by understanding temperature, pressure, composition, deriving a reservoir brine, because we understood about the formation, and taking that wellhead sample, coming down. So that's kind of how you get a scale tendency. Okay. Throw that one away. This was a well in Australia, and it was corroding. And our client came to us and they said, okay, we're seeing like really crazy behavior. we're seeing carbonate scale in this horizontal section of pipe. And then as we're bringing it up, we're seeing all corrosion here. We have no idea. We don't really know. So this is kind of like another detective, right? We don't really know. Should we change the metallurgy? Should we treat it? What should we do? You know, is it a particularly aggressive scale? Maybe we need to punt. So, and by the way, your slides were wrong because in the slides that I sent, I had the water sample. That water sample is okay. So what we found was that, okay, well, this was really a case of alkalinity not really helping us because alkalinity was dropping. Why was alkalinity dropping? Alkalinity was dropping because as we head back to that place in here and the pressure was dropping, carbonate scale dropped. So carbonate scale dropped, but it wasn't bound, the carbonate wasn't bound in the solution anymore. So pH is dropping, right? So that was one thing that happened. And then another thing that happened is as we came up that vertical pipe, it started to condense, and that further diluted the alkalinity and the pH. So if you look at the graph, you can see that the pH just kind of went nowhere. It's this lower one. So the pH just kind of went as first the carbonate left, and then the water came and diluted it. And the end of the moral of the story was that it was CO2 erosion caused by what? Caused by lack of alkalinity, you can see. And from that, they were able to determine how to treat it so that they didn't have to replace the tubing that they had, which was really good. And that's another way to apply the scale tendency, really. That's all we're doing. And we were looking at the changes of water and what scale is forming as we went along. Okay. This is an interesting one. This was in Angola. And what we were trying to do was understand, they knew that they had injection water. So this is a little bit like fracking. They knew that they had an injection water and they knew that they were injecting seawater because they didn't have any underwater. And they were going to put seawater into the formation. And they were a little bit worried about barium sulfate because, as Steve said, barium sulfate is really very insoluble. And so they wanted to, and they knew already that they needed to do sulfate removal of their injection water. So they were already going to treat their injection water so that they wouldn't blood. And they wanted to know, how could they mix the waters? What was the safe ratio? That was the question. Very bad news. The answer. So what we wanted to do was we simulated the mixing water. So we calculated what at saturation the formation water would be. How did we know the formation water? Well, we knew where they were. They were in Angola, and they were offshore. And we know what the formation is of the wells that we were treating there. So that was an advantage. Again, it comes back to my question. We go into the Marcellus share what the formation is. Because then what we did, since seawater was the only water source, we were able to calculate by mixing waters, and we did all these percentages. So we said, okay, if we added 0 to 100% seawater, is there any chance that we could leave the 2,700 milligrams of sulfate in the water? No, no chance. Don't do that. You look at where your scaling tendency. This is scaling tendency. This is the percentage of seawater. That's not going to work. And we just kept running it and running it. We got down to the point where PS, 95% of the sulfate had to be removed, meaning there was no compatibility. Those waters just simply were never going to be compatible. How do we know that? We know it just by temperature, pressure, scale tendency, and then that kind of gives you a good problem description so that you can take it for treatment. Okay, that's all I'm really going to talk about. I didn't actually have an example. I wish that we had an example of some water treatment, the produced water treatment that comes after, either in disposal, particularly in trying to get rid of the water, clean it up enough so that you can get it, put it back to wherever it came from. Because we also can help there by doing specs, by kind of specking up what has to happen to get 10 parts per billion into a particular phase. And that's also something that thermodynamics can help us with. Challenges. I loved the talks this morning about water samples because fortunately it's not my field, but actually you have to have, I love this, a representative water sample. That's not always easy. It changes over time, it changes over place. You get it back in total element analysis. One of the things about working with scale tendency is that you have to translate, because we're thermodynamicists, we're working in discrete components. So you just can't tell us my total iron is 500. We have to understand, is it iron 2 or is it iron 3? How do you know that? Well, there's ways that we know that as thermodynamicists. We know if your pH is 6, then you're going to be an iron 2. If your pH is high, we know by the other conditions of whether it's iron 2 or iron 3. But still, there's a translation issue. And that's one of the challenges, is basically translating what a water sample is into ions and complexes so that you can use this tool. The incomplete data problem. We have it really easy in conventional assets in that we really feel confident with the reservoir compositions that we can make. We can saturate a system, so we can say, okay, I know that I'm in a limestone formation, I'm going to saturate it with respect to whatever solids that I know are going to be coming, that I've already known that is a known field. And that gives us like a starting goal, and then through mass balance, we can save that sample as it's coming up, and we really can have a feeling for understanding how the state is changing as it comes up. If you don't know your reservoir composition, or if you're not really sure about what exactly is the water that you're treating, that's an issue. So there's some educated guessing that you have to do. I think that the other thing about incomplete data is largely gone, but it also can be an issue, and that's one of the reasons I was asking about water sample issues, because in the old days, when I first started in this business, people would order tests, I'll test for iron, I'll test for whatever, as opposed to just doing here's the whole enchilada of everything that I have in my water sample. And so I think that mostly we don't do that anymore, but that used to be a problem as well. And I love the idea of don't collect your sample in a soda pop bottle. That's a good tip. That leads to operational challenges. And then the other thing that I wanted to just touch a little bit about is what we've seen about applying these ideas to unconventional assets. As I said, for things like fracking or disposal, no problem. We see the same kind of issues of mixing waters. And for cleanup of water, what's less clear to us right now as consultants is the fluid flow back is less certain. We heard a statistic at a recent conference, I don't know if it's true, but the people at the conference seem to think it was true, that 80% of the fracking water disappears, never comes back, at least doesn't come back in any kind of logical time that you can correlate it. And when it does come back, it's kind of like, well, whatever, That's a challenge. So we're really trying to understand, if we don't use mass balance as one of our tools, as thermodynamicists, remember I said that once we understand the state of the system at one point, we can understand the state of the system at any point. But we really have to have the state of the system at one point. And what Steve was saying, we can't rely just on that water sample from the surface, because we have no idea what happened to it on its way up, on its way out. So that's a challenge. Can we assume, that she would say cannot, we say can we assume? We've worked a couple of unconventional assets with a particular client. One of the things that we found was that the scales that he was being impacted with are not the same scales that barium and chloride didn't. Really just kind of blew our minds up how really barium and chloride. So I guess there was no sulfate and barium and chloride became a player, but we don't see that, and that's, so we get back to the scale tendency programs. If your scaling tendency is barium chloride, good luck with most scaling tendencies. That's one of the reasons that speciated model is the high end. And then finally, operational challenges. Don't put your sample in a soda pop. Don't get it exposed to air. A lot of, trying to get an operator to do something that didn't get done, things like that. Those are kind of life challenges. I'm going to switch to corrosion. Before I switch to corrosion, I can take questions, or I can just keep. It's kind of a natural break. So I'm going to just keep going. Okay. I'm going to do the same thing, but remember I said applications and scaling, we are in the applied area of science 100%. Applications and what I'm going to present to you with corrosion is much more in the little bit more of the research phase. It doesn't mean that it can't be applied, but it's a little bit more esoteric, and you'll see what I mean. Okay. This is OLI's work in corrosion. We say that to really understand the chemistry component, we're not talking about erosion corrosion, we're not talking even about high velocity assisted corrosion. We're talking specifically about the corrosion that's in contact of the chemistry in the bulk solution with the contact surface. So that's a specific kind of corrosion. And what we say for that is if you have the chemistry in contact with the bulk solution, you need to understand the solution thermodynamics. I gave you one of our corrosion examples where we had corroding in that pipe and they wanted to replace the pipe, because usually when you work with metallurgists, metallurgists just don't really care about the chemistry, they care about the metal. So if they see corrosion, they say, oh, I've got a service and it's not good with the metal, so I'm going to change the metal. That tends to be a metallurgist's answer. So OLI is saying, well, okay, first let's understand what the solution thermodynamics is and can we change the solution as opposed to changing the metal. So that's kind of where we start. Then we say that we can actually understand what we call the thermodynamics of corrosion. We can understand whether a particular solid, let me show you that. We can understand, for example, on this graph, this is a Pourbaix diagram. When Pourbaix created his diagrams, recently, I think in the 60s, not so recent, he assumed water activity of 1. What does that mean? Remember when I showed you about, I said that there's the reference state, and then over here there's the excess properties, so thermodynamics, and a lot of, by the way, the scale of tendencies in the beginning weren't taking enough of the activities into account, because you can't just work on equilibrium. You have to work on equilibrium plus excess properties. Well, Pourbaix was working on equilibrium. He was saying water activity 1, meaning we're not going to worry about ion-ion interactions. So what we have here is what we call real solution theory. That means that we're taking ion-ion interactions into account. So the green, very easy for people like me to read. Remember, I'm a software developer, not a corrosion scientist. The green is passivating. That means that it's a protection. Why is, who said, I think Vince said, a little bit of scale is good. A little bit of scale protects your pipe. It's not the best coating, but it's not the worst coating, right? So the green areas are going to be passivating films. The white areas are going to be corrosive films. And the gray areas are going to be inert. And that's kind of a way to boil down what Pourbaix did, and what OLI adds to it is the ion-ion interactions. And that's what we call the thermodynamics of corrosion. So just by understanding the species and understanding whether they're passive or inert, we can predict, okay, you know what's missing from this? Then we usually have a line. There's usually a line that says, the natural pH of your solution is, let's say, 5.5. Then you know this line is, these two lines are where life occurs. These dotted lines, life occurs between here. If you're below here or above there, you're not on Earth. So we're just like looking right in here. You're not working with a solution that's kind of in our atmosphere. So if we're looking right in here, we would say, okay, well, if we can get above, if we get electrical potential up into this area, then we're in the passivating region. But if we get less electrical potential in our system, we might have a corrosive situation. That's how you read those diagrams. Okay, let's go back to our tower of power. So OLI says, first understand this chemistry. Then they say, understand what's activate, what's passive, what's corrosive, and what's inert. Then understand transport properties, so that you can understand diffusion between the bulk solution and the contact. If you do these 3 things, transport properties, thermodynamics, and thermodynamics of corrosion and solution, those are first principle corrosion model. So what's what we're looking for? OLI, electrolyte thermodynamics, you're looking for a first principles model. When you get into general corrosion, you're actually looking at a kinetic model. Didn't I just say kinetics are not part of the corrosion, or not part of electrolytes? Thermodynamics, they're not. But in this case, you have to. You can't go anywhere unless you've created a kinetic model of corrosion. We also have created a localized model of corrosion, and then also we can study welds. So let's recap. This is the thermodynamics of corrosion. Transport properties are just calculating viscosities, diffusivities, mobilities, and things like that, which are all kind of part of the thermodynamic framework. And then this is a polarization curve. Polarization curves are very hard for me to understand, but what they're doing is each one of these lines is connected to a ion constituent. And as they drop, that's the limit of diffusivity. So you come out here, and because we calculate that fully speciated model, we can give you each one of those lines are just basically saying, this is how far the ion is going to hit the wall before it stops. And from that, if you interpret that, what you're getting down here is we're saying by these two lines, so if you take the line that's the most furthest out, so this is the H ion and then this is the O2 ion, these two lines, which are the two active, or you could say free concentrations in the solution, are causing 53 plus 40%, 93% of the corrosion in this point is due by H plus and oxygen. Well, H plus PS, that's low pH. So that's how you read the polarization curve, and that's one of the things. Usually you get these in the lab. Usually material scientists would produce this in the lab, but you can generate it if you have a good thermodynamic model and a kinetic model on top of it. The kinetic model is basically determining these diffusion limits. And this is just an example. So from that graph, we can basically calculate a corrosion rate. So from all those underlying species and the contributions that each one of those species is giving into the corrosion model, we can calculate a corrosion rate. And this is a typical corrosion rate calculation. And what we're looking at is a passivating film. As more nitric acid forms, we're moving into a passive state. So the corrosion rate gets high, and then drops and becomes over. Would I believe this? Is this something that I would take to the bank? I think that because what is it based? It's based on a kinetic model on top of thermodynamics. It's very theoretical. What we've come to understand is that maybe the corrosion rate of 1, maybe I'm not going to say, oh, my corrosion rate is 1 millimeter a year. But what I can say is, if I'm going to add more nitric acid, I'm going to be protected. So that's kind of how to read these. That's kind of how to put it into a general rule of thumb that you can take to someone who is maybe a specialist and say, well, I have a feeling that we're going to get a passivating film the more nitric acid we can add. So that's how believable I feel it is. I think it's good to show trends, and I think it's good to show the underlying activities. Okay, we're getting close to the end. What's this? On top of everything else that I told you about the corrosion model, which is getting a little esoteric right now, one of the things that we are doing is we're calculating something called corrosion potential. Corrosion potential is the tendency for a pit to form. And then we calculate something else called passivation potential. Passivation potential is the tendency for a pit to fill. What we say is that if a pit forming corrosion is faster than a pit filling passivation potential, you've got a localized corrosion regime. Who cares? Well, localized corrosion is about 1 million times more difficult than general corrosion. You really don't ever want to have a surface that's going to cause localized corrosion. Well, how can you protect yourself from that? So you can just say, okay, you can calculate a corrosion potential, you can calculate a passivation potential. Where are they? Where are they relative to each other? The blue line is the localized corrosion regime. Why do you care? What does that do for you? Well, you can run it through and you can say, oh, that's interesting. I'm in a localized corrosion regime. I know that I was before. Or something's not going to work. So I know it, but I've got to change it. So that's another kind of aspect of trying to apply science to a corrosion situation. And at this point, I should probably say that a lot of corrosion is based on monitoring, inspection, and experience, because this is really, as I said, it's more of a research tool than it is in practical application. But what we notice is that this kind of check is pretty easy to do, and it can basically get you talking to the person that can help solve the issue. Okay. I didn't know this slide was in there. Excuse me. I just skip that slide there. This is interesting too. were, I think I had hidden those slides. They're both just applications of the model in a field that I didn't understand enough about where they were coming from to talk about them. So I'm going to skip that one too. And I'm hoping that I'm going to get to something that I recognize. Okay. I think I'm going to just skip. If you have questions, you have them in your slides, obviously, or maybe you don't. Maybe I'm the only one that has them. But I need to basically study them before I can give you any kind of cogent information on what they are. I think they were more applying our theory into different kinds of metals over different kinds of conditions. Let's talk about something more solid. Let's talk about how can you do it in industry? And this is one thing I want to talk about before we go further. The science of fluid dynamics or fluid flow, is such a different discipline. It's its own discipline, so that when you're doing pipeline work and you're trying to understand scaling or corrosion of a pipeline, it doesn't really matter whether you're scaling or corrosion. Thermodynamics doesn't have a lot to say about that. So you really have to, if you're going to try to use more science in that approach, you have to partner with a fluid flow model. And then from the fluid flow model, at a given condition. So if you had a pipeline, you could say, okay, at this temperature and pressure, because thermodynamics always relates back to temperature and pressure. So at this temperature and pressure and this flow regime, because the flow regime is being calculated by the fluid flow people, what's the state of the corrosion? What's the state of the scaling? So that's really what OLI says about the science of corrosion or scaling in pipelines. It's a really important point. People will say to me, well, can you do it in a pipeline? Well, yes and no, but if you're doing pipeline work and you're worried about the flow of the pipeline, you really need to be in a fluid flow pipeline situation. Okay, so I said before, we're looking at the chemistry analysis of the bulk solution in contact with the metal surface. That's what we involve for corrosion. Okay. We were involved in a very interesting case that took months of time, because partly we didn't know the formation, which was kind of crazy because we were in tough gas production in a northern field that had a particular formation that we didn't understand. And within 6 months of service, they got top-of-the-line corrosion found to the point of failure. It was in the cutter, and they tried to understand why. And so we were called in. What could electrolyte thermodynamics result from that? So what we did was that we had to understand what were the reservoir conditions, what were the conditions in the pipeline. We did use a pipeline program to try to understand it better. We did finally have to recreate, we did a series of comparative likely reservoir scenarios to try to pick what was the scenario that would make the most sense. And what we actually found out was we found out that good old acetic acid had been in 2 different places. It had been used as the final cleanup. Like, oh good, the last thing I'm going to do is flush everything out with acetic acid. Wrong answer, because the acetic acid then gets down into the formation and comes back. GOH is acetic acid that was also naturally occurring because they couldn't account for that much acetic acid. And basically, that was the top of the line corrosion. Well, the good news is that that cleanup with acetic acid was done. And although they still had acetic acid in the well following that, it wasn't going to be, the 6 months was kind of like the goodbye present from the depletion fluid people where, okay, well, thank you, but they were able to just replace the top of the line corrosion. They didn't have it anymore. It was failure, it was pitting failure. But what we were able to understand is that where it happened in the pipeline, how we even tried to understand it was that we could tell by temperature and pressure in the pipeline where did the acetic acid condense, and where the acetic acid condensed is where the top of the line corrosion finally occurred, which is how we finally solved it, and we were able to successfully get them back in operation without having to change the entire equipment. Okay, the challenges in this level of science, the corrosion, is that it's a research tool rather than an operations tool or an applications tool. Highly recommended for studying trends. Wouldn't really trust an absolute amount from it at this point because you don't really understand what's going on in the field versus what's going on in chemistry and science. That is a kinetic model that that we saw that was calculating the corrosion rates, and it's being developed through a subset of chemistry and alloys. You always need to have a fluid flow model. If you're going to model pipeline flow, you can't get anywhere unless you have that. We believe that unconventional assets and conventional assets are going to have similar corrosion issues. Again, we've been working a little bit in this area, and we see it as the same. We see that the approach is the same, so there's nothing, we don't have any added challenges that we can tell at this point. Okay, this is the summary. So, electrolyte thermodynamics could provide value added for scale analysis, especially in conventional assets, certainly in water treatment and water mixing. We need more experience to understand how can we work with the fact that the fracking water disappears. How can we get a state without that? I'm confident that we're going to figure it out, but we don't quite have it yet. We're still working with individual clients on that. We see corrosion simulation in this particular model based on chemistry analysis. It's still primarily a research tool. There's a huge value, however. Having said that, let me say that it's so important to understand your speciation. From our point of view as electrolyte thermodynamicists, what would you expect? But it's really important to understand what's going on in your underlying anodic and cathodic half reactions. That's where I showed you that graph where you saw those humps. Well, if you understand those humps, that's like a huge help to corrosion as a person who could just say, oh, look at this hump, that's the problem. Chemistry and alloys, we get to know more and more about them every day, and we believe that conventional and unconventional corrosion needs to be the same. Thank you for listening.
We have time for